Okay, so today's review is about quadratic inequalities. So we're going to talk about three things. We're going to talk about graphing quadratic inequalities. We're going to talk about graphing systems of quadratic inequalities, and then also talk about solving quadratic inequalities. So I have an example here to start us off, and it asks us to graph y is less than x squared plus 4x minus 5. And the first thing that you always want to do when you're graphing a quadratic inequality is to find the vertex. I think that that's the most important point that you can find. It helps us center our graph and know where else we should be looking for points. So the way to do that is you start by finding the x value of your vertex by using negative b over 2a. So in this example, my b is 4, my a is 1. So I have negative b, and my b is 4, over 2 times a, and my a is 1. So I have negative 4 over 2, which is negative 2. So I now know the first half of my vertex. What I need to know now is what the y value of my vertex is. And so we are going to plug in our x value in for y. And you'll notice that we're not going to worry about the inequality right now. We're going to just treat this as if it's an equation. So what is y when x is negative 2? And so that gives me 4 minus 8 minus 5, which is negative 4 minus 5, which is negative 9. So now I have the rest of my vertex. And so I'm going to go ahead and plot that point, negative 2, and then 1, 2, 3, 4, 5, 6, 7, 8, 9. And so there's my vertex, and that also means that that's where my axis of symmetry is. So any point I find after this, I can find its matching pair point by thinking about folding this over the axis of symmetry. So another point that I find can be helpful is the Y-intercept. Sometimes the vertex is the Y-intercept, and in that case, you just pick a number to plug in. Pick 1 or pick 3 or whatever value is near your x value of your vertex, but not the x value of your vertex. But in this case, we can see clearly that our y-intercept is negative 5, because if we plug in 0 here, it knocks this and this out. And so we get that our y-intercept is 0, negative 5. So I'm going to count 1, 2, 3, 4, 5. And there's my y-intercept. And then I want to go ahead and say, okay, well, this should be the same distance from our x value of our vertex. There should be a matching point over on the other side. So this is 2 from the midline here, and we should be able to go 2 in the other direction and get a matching symmetrical point. So I'm going to mark my other point right here. And so a lot of times that's enough points, but let's say that those points were really close together and didn't give us a very good image of our graph. We might plug in another value. For example, I might plug in 2, and if I did that, I'd get 2 squared plus 4 times 2 minus 5, which would be 4, plus 8 minus 5, which would be 7. And so that would give me the point 2, 7. And so I could plot 2, 7, and then I could also plot the matching point on the other side. So 1, 2, 3, 4, it's 4 over from the vertex. So I could go 1, 2, 3, 4 and get that matching point. So the next thing I'm going to do is I have to decide 2 things, and they're both very important things. One of them is whether or not we are going to use a solid line or a dashed line. And another thing we have to decide is where to shade. And so when I look at this, I am going to look at this value in particular, this inequality symbol in particular. And I'm going to ask myself, if I plugged in one of these values that is on the parabola, like this point, this point, this point, this point, and this point, they're all on the parabola. If I plugged them into this, would that make that statement true, or would that not make the statement true? And so, for example, if I plug in 0 and -5, I get 0 plus 0 minus 5. So I get -5 is less than -5. And I have to ask myself, is that true? And the answer is no, because it says less than and not less than or equal to, this point is not actually included in the solution set for this inequality. And that's always the case. When we have a less than or a greater than, those values that are on the parabola are not a part of the solution set. And so that means that we are going to use a dashed line. And so hopefully you know why you're using a dashed line, so you don't have to memorize it as a rule. But if you were to memorize it as a rule, if you had greater than or equal to, or less than or equal to, that would be a solid line. But if you just have regular greater than or less than, that's when you're using a dashed line. And again, the reason is because in a dashed line, you're saying that those values on the parabola are not a part of your solution set. And then the next thing is to decide where to shade. And so there's two areas you might decide to shade. The first is in between the two sides of the parabola, which is above the parabola, or you might decide to shade below the parabola, which is outside here. And a lot of times people can just look at this inequality and say, okay, this says less than, so I'm going wherever my line is, I'm going below it, and go ahead and shade. Other times it's easy for students to get confused, and so what I encourage is to use a test point. So you're going to pick any point that is not on your parabola. And so it's very important that you choose something that's not on your parabola. My favorite is 0, 0. However, sometimes 0, 0 is a part of your parabola, and then you have to pick something else. But I'm going to pick 0, 0 because that's a good point. It's not on my parabola. And you are going to plug it in to your equation. And so if I do that, I get 0 is less than 0 squared plus 4 times 0 minus 5, and I get 0 is less than -5. And I have to ask myself, is that true? Is 0 less than -5? And the answer to that is no, that is not true. So what that means is that 0, 0 is not a part of my solution set. So that means that I do not want to shade anything in between here because 0, 0 is not a true statement. So I'm going to shade the other side. And so I can just go ahead and look at my graph, and I'm just going to shade this whole area outside. Now, if I wasn't sure if I was doing it right, I could always test a second point. And so, for example, I could choose 1, 2, 3, 4, 0. And I could see if that's true. And so that would give me 0 is less than 4 squared plus 4 times 4 minus 5. And that'd give me 0 is less than 16 plus 16 minus 5. And we know that that is true. And so again, that reinforces that we're shading wherever this point is. We're shading everything that's with that point. So the test point is key. Now, like I said, sometimes you might just look at this and be like, okay, it's under the parabola. Well, here's under my parabola, and then I include everything to the sides as well. Okay, so when you're graphing a system of equations, the process looks pretty similar. You're going to start by graphing each of the inequalities separately. And so when I look at this, I'm going to start by calculating the vertex. And so in that negative b over 2a, just like we did on the last problem. And so we get 0 as the x value of our vertex. And when I plug in 0, we get -4 as the y value of our vertex. So here is my vertex. And so I have part of my graph, but I need some more points. Normally I'd go to get a y-intercept, but in this case, 0, -4, the vertex is the y-intercept. So what I'm going to go ahead and do is I'm going to plug in 2. And so I get 2 squared minus 4. Now, why did I choose 2? It's just a couple of points over from the vertex, so it's bound to give me some helpful information. And in fact, it's even more helpful than we could have imagined, because that turns out to be the x-intercept. Now, you may or may not have realized that when you were solving it out, which is okay. But there's my ordered pair. And then I want to find the symmetric point over on the other side. And I decide, do I use a solid line or a dashed line? And because we have a greater than or equal to, we are going to use a solid line for this quadratic. And there is my graph for the first one. Now I also need to figure out shading. And so, as I said last time, my very favorite point to check is 0, 0, and that one is not on the parabola, so I can check it out. And I get 0 is greater than or equal to -4, and as I think about that, that's true. So, we are going to shade where 0, 0 is. And there I go. Now, I'm going to go ahead and do my other quadratic inequality. And so as I look at that, I'm going to do -b over 2a. And that gives me +2. And so I have the first part of my vertex. And I'm going to plug that in. I see a lot of mistakes with order of operations here. Don't forget that we are squaring the x, and x is 2. So when we square 2, we get 4. But because we have a negative here, it's -4. So we have -4 plus 8 minus 4. And it looks like we get our vertex at 2, 0. So there is my vertex. And now a good point we always like to get is our y-intercept. And I know that that is -4, because that's what you get when we plug in 0. And so 1, 2, 3, 4. Oh, look at that. This graph is almost right on top of each other. And I want to get my symmetric point as well. And so there it is on the other side of the vertex. And I'm going to decide whether or not to use a solid line. And it looks like, because I have just greater than, I am going to use a dotted line or a dashed line. And so here is my dashed line. And then I want to go ahead and do a test point. And I always like 0, 0, and this one will work for this as well. So we have 0 is greater than, we get 0 plus 0 minus 4. So we get 0 is greater than -4. And that statement is true. So I am going to shade where 0, 0 is, which is all the way right here on this side of our graph. Right? And then over here on this side of our graph, it's all the way around our graph where 0, 0 is. And so with a system of inequalities, we want to know where both equations are true. And so our final answer is not the graph with just both of these shaded on top of each other. The final answer is where we actually shade where both equations are true. And so when you look at that, you can see that it's right here where we have both red and blue shading, and that continues all the way down until right here where the blue shading stops right here. So even though the red shading continues, it's not both. It's only both up until here. And so that tells us our final shading of our answer is this space right here, and we stop at the blue line. So we stop right here, and this is our final answer, where our two graphs overlap. And so I am actually going to go ahead and erase this other shading because that's not a part of our final answer. That was just helping us get to our answer. And so after carefully erasing, this is what our final answer would look like. Okay, so we've talked about graphing quadratic inequalities, and now we're going to talk about solving. And the good news is, just like graphing is basically the same as graphing a quadratic with a couple extra steps, same idea here. It's just like solving a quadratic, and there's a few extra steps. But what I would do first is I would just treat it like it's an equation, and I would just write it like this, because we just need to start by figuring out what is x if this equals 0. And so I'm going to go ahead and factor this. It factors out quite nicely. And so we get x times x minus 5 equals 0. And we can go ahead and split that up. So it looks like this. And so we get what normally would be our two answers, x equals 0 and x equals 5. The difference is now that we're not just looking for an answer that makes it equal to 0, and we're instead looking for all the possible answers that makes it less than 0, we're going to have a range of answers. And so typically the 0 and the 5 are the bounds of our possible answers. And so what you're going to start off by doing is drawing a number line, and you want to make sure that you can see 1, 2, 3, 4, 5. You can see both of those boundaries on your number line. So now that I can see them, I want to mark them with either an open circle or a closed circle. And the idea is, do these values make this statement true or not? And if I plug in 0, I get 0 is less than 0, which is not true. So that means that it is not included in our solution set. It's just the edge of our solution set. And so I'm going to put open circles on 0 and 5. And the rule, really, it's not just a typical rule, it is the rule, is that when you have less than or greater than, you're going to use open circles. And when you have less than or equal to or greater than equal to, you're going to use closed circles. And then I want to go ahead and test something that is in between my boundaries, right somewhere, one of the numbers in here, and a number that's outside my boundaries. So I'm going to go ahead and test -1, I'm going to test +1, and I'm going to test 6, and just see if I get true statements or false statements. So if I test -1, I get -1 squared minus 5 times -1 is less than 0, which says 1 plus 5 is less than 0, which says 6 is less than 0. And we know that's not true. So I'm going to go ahead and put a little X here because we're not going to shade that area. Now I'm going to try plugging in +1. And so I get 1 squared minus 5 times 1 is less than 0, which is 1 minus 5 is less than 0, which is -4 is less than 0. And that is true. So I'm going to go ahead and shade everything that's in between my two spots. And then I'm going to try plugging in something on the outside. And so I get 6 squared minus 5 times 6 is less than 0. And that's 36 minus 30 is less than 0, which is 6 is less than 0, which we also know is not true. So this has figured out all of my possible solutions. All of my solutions are any of the numbers between 0 and 5, but not including 0 and 5. And so I'm going to write my answer as an inequality. So I have x, and x has to be greater than 0, and it has to be less than 5. and that set is the set of my possible solutions. It's really important to notice that because I have the area shaded sandwiched between 0 and 5, that my x is sandwiched between 0 and 5. Okay, so on this one, as I start out, just like on the last one, I am going to write out my problem as an equation, and I'm not going to worry about the inequality part just yet. But I do need to make sure that my quadratic is set equal to 0. And then I can use any of my favorite ways to solve quadratics. And my favorite way is factoring. I always feel like if it factors, that's the fastest method. If not, we can use the quadratic formula, we can complete the square, or we can solve by square rooting. But this one, it does factor quite nicely. And so we have x minus 4 times x plus 2. And we can split up our two factors to find out that x equals 4 and x equals negative 2. This gives us our two numbers for our number line. So we have 0, 1, 2, 3, 4. Let's add 5. And then we also have negative 1, negative 2, negative 3. And so on our number line, I have to decide whether to use a open circle or a closed circle. Because it can equal, because it says greater than or equal to, I'm going to use a closed circle. So I'm going to go ahead and draw that on. And now, just like last time, I am going to test some points. So I'm going to test one to the left. So I'll test negative 3. And so I get this. And so that's 9 plus 6 is greater than or equal to 0. And we know that that is true. And because that's true, I am going to shade that section of the number line. And so now I'm going to test something in between. And I'm going to go ahead and test 0. So if I plug in 0, I get 0 is greater than or equal to 8, which I know is not true, so I'm going to put an X in the middle to tell myself that I'm not going to shade there because that was a false statement. And then I'm going to test something to the right, and so I'm going to just choose 5. And if I do 5 squared minus 2 times 5, and you know what I'm just realizing is that I have a mistake over here. This was not supposed to be 0. This was supposed to be 8. Right? Because in the equation, it was x squared minus 2x is greater than or equal to 8. Sorry about that. But the good news is that actually didn't change our work because 15 is greater than or equal to 8 is still a true statement, so it's still shaded there. Okay, so continuing on, we have 25 minus 10 is greater than or equal to 8, and 15 is greater than or equal to 8, and so I'm going to also shade where 5 is. So I see on this one we have two separate sections of shaded area. All the answers that are less than negative 2 are possibilities that make this statement true, and then all the answers that are greater than or equal to 4 make this statement true. When I have two sections of shading like this, I'm going to have two separate inequalities. And so I'm going to say, okay, x can be less than or equal to negative 2, and x is greater than or equal to 4. Either of those sections gives me solutions that make our inequality true. So I have two separate inequalities because I have two separate sections. All right, so that's it for quadratic inequalities. Don't forget to come see me if you need some help. Have a good one.